A very powerful proof technique is known as mathematical induction. It is very important to state up front that mathematical induction is not a new logic or a new technique that we cannot establish by other means that we have seen so far. In fact, this is all what mathematical induction says, and we can establish it as a quantified formula. So what this is saying here, if you look at it, imagine that we have this propositional function P of n. Okay, so we have the propositional function P of n that we are defining, for example, over all the natural numbers, or let's look at them as 1, 2, 3, and so on. Okay, so for n greater than or equal to 1. So what is this saying? What this is saying is that imagine that you proved that P of 1 is true. Okay, so whatever that propositional function is, imagine that when we plug 1 into that function, we get the value true. Also imagine that we prove the following, that if you take an arbitrary k, okay, an arbitrary k that's greater than or equal to 1, then P of k implies P of k plus 1. Suppose you can prove this for an arbitrary k, that once you assume P of k is true, you can show that P of k plus 1 is true. These two combined, the fact that P of 1 is true, and the fact that for an arbitrary k, P of k implies P of k plus 1, we can conclude that P of k is true for every natural number k, or in other words, for every n greater than or equal to 1, P of n is true. Again, here I'm assuming natural numbers or the numbers I'm dealing with are 1, 2, 3, and so on. This is all that mathematical induction says. And if you look at this, again, this is a propositional proposition that has quantifiers in it. So this is not new type of logic. And the question is that why is this true? Why is it true that if we establish P of 1 and we establish that P of k implies P of k plus 1 for an arbitrary k, then all of a sudden we have proved P to be true for all numbers? And the proof here actually makes use of this very important assumption or fact that the set of positive integers is well ordered. Okay, so we are looking at the set of positive integers 1, 2, 3, and so on. Remember that we are assuming that P of 1 is true, right? So this is by assumption. This is the assumption that P of 1 is true. Okay, and we know that for an arbitrary k, we know that P of k implies P of k plus 1 for every k. And we want to show this is also given. This is assumption. Okay. We want to show that for all n, P of n is true. But suppose that's not true. In other words, suppose we want to prove this by contradiction. So now we say in order to prove it by contradiction, we assume that for all n, P of n is false. Okay? And here let n star, for example, be the smallest positive integer such that P of n star is false. Okay? In other words, we are saying for all n, P of n is not true. This statement is not true. So there must be at least one n for which P of n is false. And I'm saying let n star be the smallest such n. Okay? Now, n star is for sure not equal to 1 because P of 1 is true. Right? Now, since n star is the smallest positive integer and it is not 1, then we also know that that P of n star minus 1 is true. Right? So if n star is the smallest value for which P of n star is false, then the number before n star is P of n star is true. Now that n star cannot be 1 because again we assume P of 1 is true. But now look what happened here. We have P of n star minus 1 is true and P of n star is false. This means P of n star minus 1 implies P of n star is false, right? Because this is, we are talking about P of n star minus 1 is true, P of n star is false. True implies false is false. So what did we get here? P of n star minus 1 implies P of n star is false. However, this is a contradiction. This contradicts the assumption that P of k implies P of k plus 1 for every k. Because when k was n star minus 1, then we got this to be false. And here's where the contradiction is, right? So these two assumptions, that P of 1 is true and P of k implies P of k plus 1, if we assume that P of n is false for some n, then we can look at the smallest such n, and then we establish a contradiction by showing that P of n star minus 1 implies P of n star is false. Now, where did this important fact come into this picture here, that the set of positive integers is well ordered? Remember, the definition of well-ordered set is that if every non-empty subset of the set has a smallest element or the least element in it. And the fact that I could say let n star be the smallest positive integer, this comes from the fact that the positive integers are well ordered. Because, for example, if I'm trying to prove this in the set of all negative integers, I couldn't say that let n star be the smallest positive integer. The negative integers are not bounded from below, and that smallest integer might not exist. So this is why this quantified formula of P of 1 and P of k implies P of k plus 1 for every k implies for all n, P of n is true. It comes from this simple assumption or simple fact that the set of positive integers is well ordered. Now, using mathematical induction in general is very simple. We need to establish two things. One of them is that we need to show that P of 1 is true. This is what we call the basis step or the base case. And then we need to show that if you give me an arbitrary k and you tell me that P of k is true, I need to show P of k of plus 1 is true. So these are the two things we need to show, that P of 1 is true and that P of k plus 1 is true when P of k is true. Once I show these two by the mathematical induction principle, it follows from this that P of n is true for every n. Let's do a few examples of using mathematical induction. So here, for example, I want to show that for every n greater than or equal to 1, the sum of the n numbers 1, 2, 3, and so on equals n times n plus 1 over 2. So we look at the base case. The base case or the basis case is that we want to show that for P of 1 is true. Okay, what is P of n? This statement here, this is P of n. Okay, well, if we want to look at P of 1, we are saying that n equals 1 times 1 plus 1 over 2, which is 1, right? So P of 1 is true. It's very easy to establish. Right? So if you plug in 1 on the left-hand side of the equality and 1 on the right-hand side of the equality, you get 1 equal 1. Then we have the inductive step. Inductive step. Inductive step say assume P of k is true for k greater than or equal to 1 and prove that P of k plus 1 is true. Okay, so what is P of k plus 1? P of k plus 1 is that the sum of the numbers 1 plus 2 plus all the way to k plus 1. In other words, we want to show that 1 plus 2 plus k plus 1 equals k plus 1 times k plus 2 divided by 2. So here I plugged in k plus 1 in place of n. If you plug in k plus 1 instead of n, you on the right hand side you get k plus 1 times k plus 2 divided by 2. Okay, but so let's look at this equality. Is this true? And the answer is yes, it is, because the sum of the numbers of 1 through k plus 1, I can say that this equals k times k plus 1 plus k plus 1. Where did this come from? This came from the fact that if you look at this here, the sum of the numbers from 1 to k equals k times k plus 1 over 2. This is equal. Where did this come from? From the inductive hypothesis. Inductive hypothesis that says P of k is true. So when we write here assume P of k is true, what we are saying, assume that the sum of the numbers from 1 to k equals k times k plus 1 over 2. So now when I look at the sum of the numbers from 1 to k plus 1, I said, okay, this is the sum of the numbers from 1 to k plus k plus 1. But by the inductive hypothesis that tells me P of k is true, I can say the sum of the numbers from 1 to k is k times k plus 1 over 2. And now I continue just to simplify this. So k, now this is k times k plus 1 times 2 k plus 1 divided by 2. And this is k plus 1 times k plus 2 divided by 2. And this is exactly what we wanted to show, that the sum of the numbers from 1 to k plus 1 is k plus 1 times k plus 2 divided by 2. In other words, we showed that P of k implied P of k plus 1. So here we showed that P of 1 is true, and we showed that P of k implies P of k plus 1 for an arbitrary k. From this we can conclude that for every n greater than or equal to 1, P of n is true. And this, the red in red, this comes from the principle of mathematical induction. If I want to show a different example now, so let's take this here, that the sum of the numbers, the odd numbers from 1 to n minus 1 equals n squared. And this needs to be shown for n greater than or equal to 1. So the base case is when n equal 1. So the left-hand side in this case here is 1. The right-hand side is 1 squared. 1 equals 1 squared. Therefore, P of 1 is true. Okay, so this is the base case. It's trivial. The inductive step assume P of k is true. Again, what does this mean? It means that 1 all the way to 2k minus 1 equals k squared. Okay, so this is what we did here. Assume that P of k is true, and this is what we call the inductive hypothesis. And we need to prove that P of k plus 1 is true. But what is P of k plus 1? Again, let's plug in on the left-hand side instead of n, k plus 1. So the left-hand side now is 1 plus 3 plus 5 plus 2k. When n equals k, it's 2k minus 1. And when n equals k plus 1, this becomes 2k plus 1. And this equals, again, by the inductive hypothesis, the sum of 1 plus 3 plus 5 all the way to 2k minus 1. This sum is k squared plus 2k plus 1. Again, this comes from the inductive hypothesis, that these two are equal by the inductive hypothesis. Okay? So we have k squared plus 2k plus 1. But k squared plus 2k plus 1 is k plus 1 squared. So now we showed that P of k implies P of k plus 1, because that's what we wanted to show. Therefore, for every n greater than or equal to 1, P of n is true. Again, by the principle of mathematical induction. Let's do one more here. We want to show that the sum of the 2 to the power 0 plus 1 plus 2 all the way to n equals 2 to the n plus 1 minus 1. Again, here we can do the base case. The base case is where n equal 1. When n equal 1, the left-hand side is 2 to the 0 plus 2 to the 1, which is 3. The right-hand side, when n equal 1, it's 2 to the second minus 1, which is 3. These two are equal. Right? Therefore, P of 1 is true. If we look at the inductive step, assume P of k is true. In other words, assume that 2 to the 0 plus 2 to the 1 all the way to k equals 2 to the k plus 1 minus 1. And we want to prove that P of k plus 1 is true. But P of k plus 1 is true means that we want to show, in other words, we want to show that 2 to the 0 plus 2 to the 1 plus 2 to the k plus 2 to the k plus 1 equal to 2 to the k plus 1, which is 2 to the k plus 2 minus 1. Again, we can start with the left-hand side here, and we have 2 to the 0 plus 2 to the 1 plus 2 to the k plus 2 to the k plus 1. By the inductive hypothesis, we know that the sum of these numbers is 2 to the k plus 1 minus 1, and then we have 2 to the k plus 1. All right, again, these two are equal by the inductive hypothesis. But 2 to the k plus 1 minus 1 plus 2 to the k plus 1 is 2 times 2 to the k plus 1 minus 1, which is 2 to the k plus 2 minus 1. Again, this is what we really wanted to prove, right? So we proved that P of k implies P of k plus 1. And by mathematical induction, again, once again, we showed P of 1 is true. We show P of k implies P of k plus 1 for an arbitrary k. Therefore, for every n greater than or equal to 1, P of n is true. Okay. Last example I want to show for mathematical induction is slightly different in terms of style here, that we want to show that if S is a finite set with n elements, then S has 2 to the n subsets. Okay, so here n could be 0, for example. It's not just about the positive numbers, but n could be 0. So if I look at the base case, when n is 0, then S is the empty set. And if S is the empty set, then S has, sorry, this should not be S has 2 to the n. This one here should be the power set of S. Okay, so if S is the empty set, then the power set of S is the set that has the empty set. And we know that this is 1, which is 2 to the 0, right? So if S is the empty set, the power set has 2 to the 0 subsets, which is 1. It has 1 subset, right? So the inductive step assume P of k is true. What does this mean? I.e., assume that if S has k elements, then the power set of S has 2 to the k elements. And now we want to prove P of k plus 1, which means we want to prove, which is equivalent to saying prove that if the size of the set is k plus 1, then the size of the power set of S is 2 to the k plus 1, right? So here, the proof, we can actually say it in English sentences. We don't have to continue just using mathematical symbols. So if the size of S is k plus 1, then let S be, for example, T union some element A, where the size of T is k. Okay, so what I'm saying here is that if S has size of k plus 1, just remove one element from S and let the other set be T, right? So T is a subset of S that has k elements, and S has one more element that we call it A, for example. Okay, by the inductive hypothesis, the cardinality of the power set of T is 2 to the k, right? Because the size of T is k, the inductive hypothesis apply to it. So the cardinality of of the power set of t is 2 to the k. But now let's look at the power set of S. The power set of S is basically the set of all subsets of t, also plus the set of all subsets of t when we add the element a to them. So the power set of S is really the power set of t. So every subset of t is also a subset of S. As well as for every set, let's call it x, in the power set of t, sorry, this one here, we say it's A union the element A for every A in the power set of t. So what am I saying here? What I'm saying is that the power set of S is the power set of t union something else. Why is that the case? Because every subset of t is a subset of S. But what is that something else? What is the other part I wrote here? Is that let's take every subset of t and add to it the element A. So now for every subset of t, we have two versions of it. That subset and that subset with the element A added to it. So now these two subsets are disjoint. P of t and the set of this set here, P of t, and the other set here are disjoint. So the cardinality of P of S is the cardinality of P of t plus the cardinality of A union A for every A. This one by the inductive hypothesis is 2 to the k. This one here is also by the inductive hypothesis 2 to the k, because here we are just doing the following. Every subset in P of t, we are adding one element to it. So we are not increasing the number of subsets in P of t. So here what we have is that the cardinality of S is 2 to the k plus 2 to the k, which is 2 times 2 to the k, which is 2 to the k plus 1. So now we showed that P of 1 is true. Sorry, P of 0 is true in this case. This n here should have been n equals 0. P of 0 is true. And then we showed that P of k implies P of k plus 1 for arbitrary k. Therefore, for every n, P of n is true. Okay?